Welcome to a course on structural dynamics using finite element analysis. This is a very exciting area, and for those of you who have so far only worked in linear stress analysis, this will really add a new dimension to your professional career. In addition, it adds the time dimension technically, so it really is an addition of a dimension. I've worked in this area now since my doctoral degree some 34 years ago, and so I'm familiar with this area and I love it very much. Some parts of it are relatively easy, namely the normal mode analysis, and to a little lesser extent the response to harmonic excitation. Then the topics can get a bit harder as you get into transient response with its numerical integration and perhaps stationary random problems. We won't consider stationary random problems in this particular course, but we will help you pretty much on the normal mode problem, the steady state oscillations, and several kinds of numerical integration in time that cover transient problems. So this is a very productive area in which to study. Now, my first lecture is primarily an introduction. I'll point out some special things with dimensions and units. I'll do a course overview, introduce myself in both personal and technical ways, review a bit on the static finite element analysis and the symbols that we used in the first lecture series on linear statics. Then we'll give an overview of the structural dynamics and the dimensions and units. In the next two figures, I'll review what the course content will be and how we will teach it. First of all, our major goal is to understand finite element theory as applied to dynamic systems. And we're going to model structural dynamic systems rather than electrodynamic, such as magnetic problems, radar problems, and so on, and in contrast to fluid systems. I'm going to use MSc Nastran as the laboratory computer program. I tend to call these laboratory sessions where we use a computer code and then we solve a physical problem. In spirit, it's very much like a true laboratory session. On the business side at the University of Michigan, I found if I treat it that way, I also am given a laboratory assistant without any question. I was a pioneer in using large-scale computer programs at the University of Michigan, and I found that as a slick trick. It must have just occurred to me in some evil moment in my dreams or something, but I asked for what was called a lab assistant in my large computer-based course, which had 100 students, and the assistants just flowed like water. Had I asked for something like a computer technology guy, I'm sure they would have laughed me out of the room at the spot. So I continue to use that word laboratory session for these simulations that we do of a mechanical system. And so my approach in this lecture series is to give formal lectures, much as other classroom lectures. Of course, these are based on a live set of lectures that I've given at the university, and I use view graphs with soft-tip felt pens and draw on those visual aids. Then that can be washed off later since the ink is water-soluble. What my son and I have done in this new technology of compact disc recording is to capture that same information on compact discs using the so-called annotation process. Now we've trademarked it as Live Pen, and this whole series is one of a personal professor lecture series. So there's a little bit of business nonsense mixed in. But it is a new approach, and I think it's the way that encyclopedic material can be presented. Our laboratory sessions will consist of these simulations of some mechanical system. And particularly in transient dynamics, we find it to be physically satisfying because you can watch that structure deform under load and see the progression. Modern visualization methods are getting so good that it's pretty easy to create what is essentially a time study of this visual image. And so it's very nice anyway to get yourself in the mood that you're actually watching something happen. Case studies will be several things that I have consulted on over the past few years. I've found that of the attendees of my live university courses and my summer conferences, that a wide range of people can profit from this material. Of course, engineers, but also physical scientists such as chemists, physicists, mathematicians who understand the linear mappings, computer scientists who are interested in the computer codes that are used and have some idea about input and output. I really more or less think of those three technical areas that are the support for this class, and those are the engineering mechanics of structures, and then secondly the mathematical knowledge of linear transformations and matrices and vector operations, and then thirdly the computer usage. So it would help if you had all three, but I've seen people get by with only one of those three backgrounds. So if you have two or three of those, then you're in good shape. This course is intermediate in level. If it's too difficult for you, you might want to back up and look at the linear static course, or perhaps review some selected subset of those lectures. I might be able to help you on a personal basis if you give me a call and ask, with your background, what lectures should you look at in the linear static series. I'll point out the course content in this next figure. We're going to have 17 lectures, and they tend to be 55 minutes. A couple of them will be a little shorter. We do study some eigenvalue theory and have 4 such lectures. That's fairly mathematical. That's very much needed for the normal mode concept, and then carries over into some other problems as well, such as forced response of linear structures to periodic forcing. Then the basic structural dynamics theory takes 11 lectures, and en route I give 2 case studies, which are industrial examples. The viewer taking this class should have access to the set of compact discs on which this is recorded. You should have a multimedia study guide on structural dynamics. There is a textbook that corresponds, not quite chapter by chapter. The multimedia study guide fortunately has every figure in the course reproduced in a comb-bound manual that's an 8.5 by 11 manual. Then the textbook is the theory underlying it all. The commercial finite element code, although I will use Nastran, the viewer might want to use some other code. I have used Mark, Astros, Abacus, ANSYS, it goes on, and it is quite possible to learn this material but use a different finite element general purpose code at your home installation. Let me give you a personal introduction now. My name is Bill Anderson. That's such a common name that there are 2 or 3 of me everywhere I go. In fact, some years ago I got subpoenaed to a murder trial, and I was just pleasantly standing in my aerospace building when this sheriff came up and slapped down a subpoena on me and said, "You will appear at the murder trial of John Jones in 1 week." And I thought, oh my gosh, what did I do now? You know, I didn't think I was sleepwalking or something. And it turned out to be another Bill Anderson, needless to say, who runs a herbarium at the university and was an expert on palm fronds, where a murder had been committed and a body found in a trunk in Detroit, and there was a palm frond clutched in the person's hand, and there was only one place or two places in Detroit, the whole Detroit area, where these palms were found. So my herbarium friend Bill Anderson kind of zorched me on that, and I had some anxious moments before I found out what was really going on. So too common. Now, I know there's a hillbilly singer with that name and everything, so I just have to live with it. Okay, my major degree was at Caltech, PhD under Y.C. Fung at Caltech. He's known pretty much today for his biomechanics and is kind of a leader in the world in tissue studies. So it's very strong nonlinear mechanics and a very tough field. My earlier work at Iowa State in my formative years was an excellent program, very motivating. Many of my friends have gone out into industry with that training and really have done well. So I had a bit of the high-powered academic view, and then I had a bit of the middle-powered with a lot of practice, a lot of good examples in the early career. I think we miss that a little bit nowadays. Many of the universities are becoming more high-powered and theoretical, and we don't tell enough war stories to people about what happened in our careers and the strange little fights that you've had or successes, both failures and successes. After getting out of the Air Force at Wright-Patt, where I served from '62 to '65, I came to the University of Michigan. I've been here ever since. Sometimes I say I've never been able to find honest work. The University of Michigan has been a fine place for a career. There are a lot of pressures in academia now. I don't know if I would say things have changed a lot, but they've changed a little bit. Universities are now very competitive in an entrepreneurial way, and so it's a very active life. It might not be quite what people expect it to be, but I've enjoyed both of those tours of duty and intend to stay active at Michigan yet for some years. Early in my career, it was possible to get summer jobs when you were a sophomore or junior. I also wheedled and begged Vought Aircraft in Dallas to let me come with them after my freshman year because they had hired my brother, and I went along for the ride. So I still have a friendly spot in my heart for the Chance Vought Aircraft Company in Dallas. It's changed names a couple times. It's been bought by Ling, and I think perhaps reorganized a second time since then. Boeing was my employer in summer of 1957. Very good experience working on the B-70 bomber proposal, ultimately won by North American, but a very heady summer and very motivating. If I had one message to send to the industry, it would be that it would be good to get back more and more to the old days when engineers were hired for summers during their college careers. It really motivates the students. I'll say it in a strange way. Students, once they've been out, like in their junior year, if they've been out for a summer to industry, have a lot more tolerance for nonsense in the sense of tough derivations and numerical calculations and so on, because they know where they're going and they know how this ends up and that it's really useful. If you haven't been convinced that all the calculations are important, then it just becomes drudgery. So I would say every young person, both the young men and the young women that are in college, profit so much from summer work that every organization out there really should try to hire somebody. The consulting I've done has been primarily at Ford and GM in terms of year in, year out. I've done a lot of consulting work at Ford and a lot of training at GM. Then my consulting company, Automated Analysis, does just loads of work with Caterpillar, and they've been just a wonderful customer. High-tech, but yet with old-time values and traditions. So that's been a good experience. And Chrysler, we're doing more and more work with. Chrysler, an innovative company, has done some interesting things in the last few years in the design area. So unlike many people in an academic environment, I really admire companies of all kinds for what they've done in spite of tremendous pressures from federal agencies, state, local, environmental, workers, managers. It seems that everybody has a bit of an axe to grind, and yet these corporations are able to continue. And it shows somewhat the durability of the idea of a corporation and that legal entity and how it can band people together for good. I think in the United States we need to rethink this a little bit. We want to keep individual freedoms, but on the other hand have strong corporations. My current feeling, which is kind of a strange one in a way I suppose for a professor, is that I'm not certain that our corporations are strong enough in the United States. When you have the largest corporation in the world, like General Motors, that makes $5 billion in a year, the newspapers go up in flames as if this was intolerable greed and almost, you know, verging on corruption. That sort of amounts to what the federal government does in lipstick subsidies or something like that. I mean, I just feel that the corporate America has gone through a period of being pasted by everybody, and they really don't deserve it. So I think we all need to be a little careful on that. I have lived in Germany for a year, and my feeling was in the early 70s that corporate Germany was a lot more powerful in terms of pricing, the employee relations in just a lot of ways, maybe a little too much the other way. There were a lot of individual people buying high-priced products, living in small homes, and then the corporate and the government offices tended to be more of the big substantial buildings. So I'm not an expert on this, obviously, but that's just a little insight to my overall feeling. I have created 2 startup companies in Ann Arbor. One of them, Automated Analysis, has now grown to 290 people in 3 states who are consultants to the numerical simulation industry. By that I mean all kinds of groups that do simulation of structures, of fluids, where you're worried about the way some system will react under load. And of course it started out in finite elements, but we now have people doing other technologies as well, and we do a certain amount of design and test. My second little company is brand new. As I speak to you, we've just gotten the patent allocated to, let's see, there's a proper word for that. It's allowed on the process by which you're viewing this set of lectures. So Little Online Training is an empty shell company at the present, which holds, I think, a kind of a fundamental patent in multimedia. And who knows what will happen to that in the future. My own hobbies, volleyball, basically. I've picked up downhill skiing 4 years ago. I absolutely love it. I used to have time to do model aircraft and woodworking and gardening, and those have kind of gone by the wayside in recent years, but I'd like to get back in those. Model aircraft, the radio-controlled aircraft are really fun. My wife's response to that personal introduction is always, "Oh, Bill, that's corny. Don't do that." Well, if you've suffered through it, it's too late now. I should have told you. You could have skipped over that. Let's look a little bit at the variables that we used and the symbols that we used in static finite element analysis. This will bring everyone up to the same speed. The heart of finite element analysis is a set of vectors for nodal properties, and nodal displacement's U, the nodal force is F. And these are what you work out the entire finite element process with. So you've by that time discretized. But really, it's hard to get those results without looking into the interior of the element and interpolating what's going on in the interior. And the interior variables are these 3 vectors here, the displacement field, the strain field, and the stress field. Those are related by classical matrices, the strain displacement law and the generalized Hooke's law. This one is algebraic. This one's a differential operator. So if you've come out of a strength of materials course, perhaps an advanced strength of materials course, you would understand the way the field variables are defined and how they interact. The strain that we're talking about will be in terms of engineering strain rather than the tensor strain, which has an extra 1/2 factor on the shearing components. So we'll use engineering strain. The Q here are a strange set of coordinates called generalized coordinates. They're the coefficients of the polynomial terms in the displacement interpolation. And the matrix that relates those generalized coordinates to the displacement field here is called phi. It's a displacement function matrix. It has a nice feature that the columns are related to the rigid body modes and the straining modes of your element. But a more modern way to look at that often is to map directly from the nodal displacements to the field displacements. And when that can be done, we use this matrix N called the shape function matrix. This is a cold mathematical matrix with little physical intuition showing, but is very efficient and is more the modern way of doing things. If you can map directly from the nodal displacements over through this strain matrix B, then you can arrive at the field strains. And lastly, to jump the entire chasm from nodal displacements all the way over to nodal forces, we define a stiffness matrix. I'll show that in the next figure after a minute, and you'll see that these are merely linear transformations that work one after the other. Now, in addition to these vectors, you have field equations. There's one of displacement compatibility, and often that's applied separately, but if we enter the problem, as we often do in the displacement method of finite elements, we first assume the displacements in the form of the shape functions, which really says that you know how to take your nodal coordinates and map them into field coordinates. Now, unless you do something really stupid on your shape functions, you satisfy compatibility identically. And compatibility implies that you have no holes opening up in the structure and no multi-valued functions where you have overlapping material. So generally we don't care that much about compatibility, and you won't see that mentioned in this course. But the one that you will hear at least the dynamic equivalent of is the equation of equilibrium. We'll call it the equation of motion when we get into dynamics. This does hold, and it brings in the force balance in the structure, both in the internal field variables at first, and then we ultimately convert that into a matrix form that relates the forces and displacements at the nodes. Your problem isn't complete, though, until you apply boundary conditions around the perimeter of your problem, and that will give you a unique solution. Let me show you in equation form the same relations that we spoke about in the previous figure. The nodal displacements U can be mapped into the generalized coordinates Q through this artificially generated H matrix, which has to be inverted. This used to be a problem in the days before symbolic manipulation, and there have been new elements generated where that was the dominant work in the whole problem, in the old-fashioned way of doing things. A more modern thing is if you can map directly from the displacements at the nodes directly to the field displacements using this shape function matrix. And this has now become the modern way to do it. If you want to express that in terms of the displacement function matrix and this artificial matrix H, it looks like this. It's a product. So it's just a linear set of operators acting one after the other. Likewise, the strain matrix can be broken into its terms of the strain displacement law, the displacement function matrix, and then H inverse. Finally, stress can be mapped from nodal displacements. This isn't sometimes given a name, but I'll call it S now. And that also can be broken into a set of 4 linear mappings in sequence. Let's review 3 of the most important equations from our linear static work. Here's the equilibrium equation. The elastic forces have come from a stiffness matrix times the vector of nodal displacements. Some external forces are concentrated in nature, and we put those at nodes, really making the mesh in a way to be sure that there's a node under every concentrated load. Other loads are distributed, such as gravitational loads or pressures, and those have to be converted into equivalent nodal loads that act at the nodes. Now, within this equation, we need to define the stiffness matrix, and that's done in 3 alternative ways. Here's the most concise way, using the strain matrix, the material law, and the strain matrix again. This Kij basically is the force generated at degree of freedom I due to a unit displacement at only degree of freedom j. When you see the nature of this expression, you see that it's quadratic in the thing that is displacement-like, and indeed it is something like a strain energy law based on unit displacements. So stiffness has basically come about from the strain energy that's calculated by unit displacements in the coordinate directions in turn. One way that that matrix can be calculated is by going into this form where the shape functions appear explicitly, and this might be a common way to calculate the stiffness. An older-fashioned way was to separate out the shape function matrix into this phi matrix and its partner in crime, h. By moving the constant h matrix outside the integral, you end up with this interior term, which is sometimes called a generalized stiffness. Argyros used that in his natural mode method, and in here you can see the result of motion in rigid body modes and in straining modes, and there are a lot of zeros in this particular form of the stiffness matrix. But today I would say most people would use the intermediate formulation. Finally, on the equilibrium law, we needed the equivalent nodal loads. We actually looked at 5 different ways that you could generate such loads. One was due to a line load, another a surface traction, another was a body force. We could have an initial strain or a pre-strain. You can have an initial stress. In each case, you're developing a work equivalent set of loads at the nodes that replace the original distributed force field. And in each case, there's something that's force-like times something that's displacement-like. And so you're finding specifically the amount of work that can be done by that distributed load on the proposed displacement field. The pre-strain here plays a unique role in that it's possible to study temperature fields and the thermal stress that they cause by calculating what the strain would have been if freely allowed to expand. So this is a very useful model here for developing thermal stress solutions. Now that we have reviewed the linear static finite element theory, let's move on to the real topic that we're going to study in this lecture series, and that's structural dynamics. So as we've said, the real change now will be the inclusion of time as a variable. Most of the ideas from statics still do hold in sort of a quasi-static way. I'll point that out in the next figure, where we show that we really use separation of variables so that the space and the time dependence uncouple to some extent. at least within a single element. And we still have the field variables. I'm showing the time explicitly to make you realize that this whole body now is jiggling, much as a big bowl of Jell-O. The nodal displacements move in time. The forces at the nodes can be time dependent. We still have the same spatial dependence here with a set of displacement functions and strain displacement laws, which basically are quasi-static in the sense that, of course, material properties and some things may change in time. Now, the material properties would be shown through the G, but at any instant of time, these mappings are not functions of time for a given problem, especially for our linear problems. So, time becomes the measure by which we tick off the solution as it proceeds along. We still have equations of equilibrium, which are now equations of motion. We've included the inertia term. Compatibility still lurks in the background, but again, since we're using the displacement method of finite elements, we rarely have trouble with compatibility, not at all in this particular lecture series. Finally, you have to have boundary conditions around the edge of your body just to choose among all the candidate solutions that might have solved the problem and to tie this down to reality to get the unique answer. Now let's talk further about how we're going to handle the time variable in the structural dynamics problem. Mathematically, we say we use separation of variables down at the element level so that the time dependence is factored out as a factor multiplying a spatial dependence. The original field variable for displacement would have been a general function of space and time and would have been characterized by a set of displacement vectors shown here at some instant of time. But we're going to assume that the displacement field is controlled by the nodal displacements, which do vary in time. And as these nodal displacements jiggle around, then the element itself has to deform proportionately. This is called a quasi-static interpolation, where the shape function carries the spatial part of the dependence, and then the time part is carried by the nodes. This implies that the disturbance speed within the element is really infinite, and it means that the motion, at least as one element, let's suppose one node on this element here vibrates back and forth. Then as that node vibrates to the right, the body will instantaneously deform and compress uniformly without any wavelets or anything transient going on in the interior. Then as the body deforms with this node going to the left, the body will follow that and end up out there somewhere. And so it's kind of like an accordion with uniformly spaced pleats that proportionately expand and contract. You might call this synchronous motion in that the body is acting in unison in that way with regard to one node moving. Now, if several nodes are moving simultaneously, then you'll get a superposition of these kinds of effects. One thing this warns you about immediately is then if you have a very large finite element in a transient vibration problem, you must be a little careful because an impact on the end of a rod will instantly be felt at the far end, giving within that single rod an infinite wave speed. It's better if you have a body that's subjected to transient excitation to divide it up into a number of smaller elements. Then you can see after the impact on one end the time progression of a wave traveling down the body with the wave speed of the material. I'll show you a figure now just breaking down the overall mechanics area into these problem types. In the first course on linear statics, we worked with rigid body displacements and elastic displacements. Rigid body displacements pretty much were considered bad because they made the stiffness matrix singular, and we eliminated them before we could get an effective solution. The elastic displacements were our goal. In dynamics, we find that we have the rigid body motion as a serious candidate, and people who work with vehicles often study entire bodies of literature, such as airplane dynamics, assuming that the airplane is rigid. So this can be a separate study on its own. For instance, the phugoid mode in an airplane flying along a path. On the other hand, there are many problems in dynamics that do involve elastic motion, such as the vibration of a tuning fork. In other situations, you get both acting at once, and a modern case in aeronautics where this happens is the so-called body freedom flutter, where at first people thought the wing divergence would only be a kind of motion that was elastic, where you could fix the wing root. But in recent years, it's been discovered that you never really get that kind of wing divergence, that you always get body freedom flutter first, where the fuselage moves up and down and then the wing is out of phase with that, and you actually get a combination of rigid body modes and elastic modes. Now, in addition, you have so-called free vibration, where there are no live loads on the structure. This leads to normal modes of structures. Then the forced vibration problem is where there are live loads. Free vibrations, due to the body's own elastic and inertia forces, is often studied by the eigenvalue theory, but forced response is a conventional input-output problem where you have a given force causing a given response. When you do have active loading on a structure, or live loading, then you can characterize the problem for these linear systems by the kind of loading. You see, the kind of response is pretty much determined by the kind of load in that case in linear systems, and so it's pretty much a straight-through shoot on terminology. If you have a periodic load, you're going to get a periodic response. If you have transient load, transient response, and so on. So we'll characterize our problem by the loads, whether these are forces in a conventional mechanical sense, whether they're thermal stresses or electromagnetics or whatever. The harmonic excitation shown here with this sine wave is a very important kind of problem in automobile and airplane design. Many of the response characteristics of a vehicle are considered by seeing how the vehicle responds to harmonic loads. It's particularly relevant because the engines in those devices are often reciprocating engines, or perhaps at worst jet engines that have a given speed and excite certain dominant modes. The more general case of a periodic excitation would be perhaps where you drive your car over a railroad track and you're hitting the ties at given spacing. Now, you wouldn't get this sawtooth, but there are problems where this could occur. Periodic solutions often are just made up by sums of harmonic solutions with the right frequency distribution. I don't study periodic solutions as a special case in this lecture series, therefore, because in linear systems it's just a superposition of solutions. Transient problems are those where the force has some finite start and stop time, and often this is a short time with respect to the system's response, and then we might call it an impulsive problem. If the single event is rather sluggish and long like this, then you might find the response of the system would approach a quasi-static situation where the restructure would just give some kind of a response at some different amplitude, but because of a dimensional difference here between the force and the displacement response. But that's a relatively simple problem for the relatively slow force changing, and that could be studied in a quasi-static way as well. Stationary random problems are like airplanes hitting turbulence in clear air, or automobiles driving over rough ground. you can predict some of the averaged values of the structural response by using this kind of an approach. Random problems, we have truly random force here, where you have perhaps no force for a while and then something that looks vaguely stationary random but perhaps goes into something deterministic and so on. This is impossible to handle, so we won't study that. By definition it's impossible because a truly random force is impossible to predict. The general structural dynamics equation of motion has 4 terms in it. We have an inertia term, a velocity-dependent term, typically damping, and then an elastic term here. Sometimes this velocity-dependent term has some gyroscopic or Coriolis effects in it. The force function here is considered to be known in the standard presentation of the equation, and then the unknown is the displacement field. Now if you're doing a transient problem, these displacements at the nodes are actually joined by the unknown variables on velocity and acceleration. So when we get to that point, it turns out there are a lot of unknowns in the time integration of a transient problem. One simple case for this equation is when you drop out this velocity-dependent term, throw away the external forcing, and you're left with a balance between the inertia forces and the elastic forces. And when you do that, you can then assume that the nodes are going to oscillate in a harmonic time dependence. When you put this cosine form into the original problem, the cosines cancel out as you go from end to end on the problem, and you're left with this static equation below here where you have only the spatial coordinates at the nodes. And then you get the balance between the stiffness terms and the inertia terms. The frequency of oscillation shows up at this point, and often that term's called the eigenvalue. There are basically 2 kinds of solution processes that are needed in structural dynamics. One of them has to do with the forced oscillation, which is an input-output problem or a response problem, and then the other is the eigenvalue problem that we mentioned. The response problems would occur when you have the frequency response. That means response to a harmonic force. Or a transient response, some kind of impulse, or the stationary random response problem. Eigenvalue problems are much different. To do those problems you need to have an eigenvalue analysis, and we're going to look at that in detail. If you've only done linear statics, this becomes a very novel idea to you. All I can say is that eigenvalues are present in the world throughout us. Some people call them characteristic numbers, latent roots. They're different names, whether you're in a sociological field or engineering or math, chemistry, and so on. But these usually are characteristic numbers that pop out of a given system. For us, it's a balance between the mass terms and the stiffness terms. If there is a Coriolis or a gyroscopic effect, then you sometimes get into complex eigenvalue analysis. This can also occur in aeroelasticity, where you have complex stiffnesses, so that the airstream is putting a springiness into the problem, and sometimes at a time phasing that makes it not look like a conventional stiffness. When I started to work on the finite element structural dynamics problem years ago, I wondered about the dimensions in units. And it took more time than I thought to straighten that out, because the system of units that was being used centered on newtons, millimeters, seconds. And then I needed to find out something about the mass unit and realized I was a bit adrift. Well, many of you may know that mass is really defined in Newton's second law, F equals ma. And when you choose units for your other quantities, notably the length, then you have to have a consistent mass measurement, which you might call a derived unit of mass. In addition, there are two approaches to how you handle your dimensions in the problem. Let me state that dimensions are different than units. Dimensions mean force, length, time, and those are the general characteristics that are handled in similitude and other dimensional analysis problems. Well, one group of people, namely structural mechanics people, tend to work with force, length, and time, and then they eliminate mass as soon as they can as a dimension in terms of the other three, using Newton's law. People in fluid mechanics tend to use the absolute system where they use mass, length, and time, and they eliminate force as soon as they can in terms of the other three using Newton's second law. So this is interesting. I hadn't even realized that we had a special name for what we were doing. Once you decide if you're working in gravitational or absolute dimensions, then you need to pick out units. The set of metric units that I've alluded to, I've now called finite element units. Those are the ones based on millimeters and seconds and newtons. And then we'll talk about the mass that is derived in a minute. The System International is a general approach where you deal with Newton second meters kilograms. And surprisingly, one of those is in a 1,000 unit at the outset, and the others are direct units. Then the System International people encourage the engineers and scientists to only use systems of units that differ by a factor of 1,000. So that means the centimeter is pretty much dead. Things like dynes and centimeters and who knows what, furlongs and fortnights, I guess. We want to use a finite element set of units, which is really a special case of the System International units. Now, we used to use conventional units in English. Fluid mechanics people do this a lot yet. That would be foot, pound, second. And then some of you know that the derived mass unit that goes with that is the slug. Many people, however, work with what I call the industrial version, which is the inch, pound, second. And then, interestingly, the derived mass unit is a so-called slinch, or a slug inch, which would, on the Earth's surface, weigh as much as 386 pounds. So when you go to a smaller length scale, like an inch, then you get a larger derived mass unit. I've put these different systems into a table in the next figure. Here I have the metric and the English side by side, and then above and below gravitational and absolute. The one that we're most interested in is this set of finite element units here, newtons, millimeter, and second. And now I have given you the answer that the derived unit of mass is the megagram. And I'm sure you're saying, big deal, megagram, basilogram, who cares? But a megagram is a metric ton, is our reference unit of mass. And the reason that people have chosen millimeter as a reference unit of length is because they don't want to use so many decimal zeros when they're defining, say, the stresses in a camera. If you're at Eastman Kodak and trying to find if your camera is going to break when a gorilla steps on it or whatever, then you want millimeters, a small unit. But now you have to, in dynamics, you've got to measure the inertia of things according to how many metric tons they weigh. So the shutter, you know, is flipping, and you say, how many metric tons is my shutter? Well, that paradox just blew me away when I started doing this work. It must be 25 years ago. And I phoned some companies and I said, are you sure you want to do this? Is this the right way? Well, it turns out that as long as the dynamicist knows they've got an awkward mass set of units, we're going to let the static stress people win this battle and use a tiny measurement scale. Here's the slinch over here that I had mentioned earlier, the slug inch, and here's the slug in the English measure. Fluids people pretty much, I think, are going with kilogram meter second. And I tend to do that on my thermal problems like heat conduction and heat transfer as well. The general purpose computer codes that are used, such as MSC Nastran, do not have embedded constants in them. So as long as the user uses a consistent set of dimensions and units, then there's no problem. So there isn't such a thing as a metric version of Nastran or an English version. For most of our problems then, we're going to use millimeter, Newton, second sets of units. If we go further though on this, in our finite element metric system, we need to talk about pressures, which basically are newtons per millimeter squared for us, but that's the same as meganewtons per square meter. And a newton per square meter is a Pascal. And so the relevant pressure scale for us, or the unit, which is a scale on this quantity, is a megapascal. 1 megapascal is 1 MP equals about 145 psi for those of you in the English measure system. I think we need to call it the American measure system now, since our country is one of the few that still uses the older English system. And it's converting rather rapidly now. But the numerical value for mass makes density be kind of a tough quantity, because that becomes Newton second squared per millimeter to the fourth when you want to convert to our system, to our gravitational system. And the proper density then is megagrams per millimeter cubed. So how many metric tons can you put in a millimeter cubed, which is a tiny, tiny little fella sitting here? So I consider that an awkward set of units. It's in terms of mass, but it's okay. We get rid of mass anyway as soon as we can. But mass is 10 to the minus 8 typically for a lot of materials. Very, very many zeros. One way, if you want to check some of these ideas, is to use Newton's second law, but put it into numerical form, and then you can see the connection between pounds of force, slinches, accelerations. Over here you have the metric version with 1 Newton is 1 megagram now times 1 millimeter per second squared. I would guess my advice on dimensions and units is to use one consistent set of units and learn how to convert from using the Newton's law in your set of units to get rid of mass when you don't want it, and so on, and then stick with that set of units. Let's have a simple problem session now where we'll look at the conversion of units from one system to another. The problem statement is that there's a certain plastic that has a specific weight, and that's in pounds force per inches cubed. But let's convert that into density in units that are suitable for finite elements, say in English pound second squared inch to the fourth, or metric in megagrams per cubic millimeter. Now, specific weight, as it starts off, has the wrong dimensions. It's not a density quantity, it's a force per unit volume as measured on the Earth's surface. So to get density, first of all, you really need to correct the dimensions of specific weight by taking the specific weight over the acceleration of gravity. Let's work out the equations for these conversions. The general law would be that density is specific weight over gravity. Then we put in the specific weight here in the English measure that was given, and then divide by acceleration of gravity 386.4 inches per second squared. When you get done with that, you have this number 0.000129 in the units pounds second squared per inch to the fourth. Now that's the thing that we call slinches. When I work a problem out, though, I always immediately get rid of slinches and put it in pounds second squared per inch per fourth, as you do in the gravitational approach, the gravitational dimensional approach. Now, if we want to convert further into a metric system, what you like to do is take something that is dimensionally correct, such as this representation here, and then change units by multiplying by 1 as many times as you need to cause the final answer. In our case, you divide by the quantity you're getting rid of, the 1 pound, to eliminate this, but we know there are 4.451 newtons per pound. So that ratio is just like multiplying the number by 1, but it effectively gets rid of pounds here with this one. We now, in essence, by putting these two terms together, have a quantity in newton seconds squared per inch to the fourth. But now we have to correct the length scale. And we know that 1 inch is the same as 25.4 millimeters. In this case, the inch appears to the fourth power. So I raise that number 1 to the fourth power and cancel inches to the fourth against inches to the fourth. And now we have our final answer. We multiply all the numbers out and we get this number times 10 to the minus 9th newton seconds squared per millimeter to the fourth. And that would be equivalent to megagrams per millimeter cubed if you were using the absolute system as fluids people would use. But structures people tend to use this in terms of force, length, and time.